Hi guys, welcome back. So today what we're going to be looking at is calculating error. So in particular, calculating the percentage error when the experimental result can be compared with a theoretical or accepted value. And we're going to do that using this formula here. Now, if you didn't know, my first name is Cassandra, and that's actually of Greek origin. And Cassandra was a prophet. And I always tell people I'm a psychic and they don't believe me. And you know what? Cassandra of Troy, she had the exact same problem. She was a prophet, but the gods cursed her so that no one would believe her. And so what she did was she actually predicted the downfall of Troy. And she said that if you do not listen to me, Troy will be fallen by tomorrow. And they said, no, that's rubbish. That's not true at all. And then what had happened? Later that day, they received a gift from a neighboring country. And that gift was a horse, a big, giant wooden horse. And they said, why are they giving us this big, beautiful horse? It must be because we're the most wonderful place in the world. Troy is just the best city to be. But what they didn't know was that there was a bunch of people hidden inside the horse. So this is the famous story of the Trojan horse. And the men at night came out of the giant wooden horse. They attacked the city, and the city had fallen, just as Cassandra had originally predicted. And the reason I tell this story is because quite often I make these psychic statements and people don't believe me. But I really want you to listen to what I have to say. My psychic prediction is that you're going to have to do some sort of experiment as part of your assessment for this term. And so you're going to have to use some sort of way to measure the accuracy of the experiment that you're doing. And it may just be using this formula. Now, you can choose to listen to wise old Greek Cassandra here, or you could choose to ignore me. That will be your downfall. So just letting you know, this is an important piece of information. So please put that somewhere that you're going to remember when you go back to do your assignment. Okay, so let's talk about what error actually is. So for your vocabulary, I want you to go ahead. I want you to define random error, systematic error, parallax error, and percentage error. And we will go through each of these sort of terms. So let's talk about first what error and what uncertainty actually is. So uncertainty, it's a description of confidence in the accuracy, and we do this using numerical values. So we have the best estimate of our particular value plus or minus an absolute uncertainty. So when calculating absolute uncertainty of a measurement, the number of digits is important. Okay, so I've got an example here of what I mean. So this measuring cylinder, and this measuring cylinder actually has the accuracy on here. So the accuracy is plus or minus 5 mil. And all lab equipment is going to have this uncertainty on it. I know that Typo was selling beakers and things for a while, and you could tell that they weren't accurate, or they weren't actually scientific beakers, because they didn't have this accuracy or this uncertainty actually placed onto the beaker. So you will see this on scientific equipment. If it does not mention what the scientific equipment actually, what the error actually is, if you have a look, now as far as I can tell, this is being measured in mils, and this is going up 56, that would be 75 there, because that's halfway in between 50 and 100. And so each of these little lines would represent 5 mil. So the way that I would know that uncertainty is I would just pick the smallest possible value, and then I would just put the plus or minus in front. So I'll do another example. So let's say I had a beaker, and this beaker measured 1 litre, and then it had a line here at half a litre, and then it had 1, 2, 3, 4. So each of those would represent 0.1 litres. So then the smallest unit of measurement that I can actually measure on this particular beaker is going to be 0.1 litres. So the accuracy would be plus or minus 0.1. So for example, if I was going to measure something that was half a litre, I would do 0.5 litres plus or minus 0.1 litres, because 0.1 is the smallest increment that I can see on my beaker. Okay, so this is just a fun little one. When I was at uni, when I was doing stats, we had to do something called an error bar. And an error bar, you can change the value, but this is like a 95% confidence interval that the mean falls within that range. So if we take a particular value and we find the mean, so let's say I was measuring plant heights, and there's always a little bit of variation in the size of plants. And I worked out their average, and then I can work out their confidence interval So this is a 95% confidence interval. So that means that there's a 95% chance that every single value of this particular treatment will have the plant's height fall within that range. So I just liked this because when I was going through uni, you know, stats gets a little bit kind of crazy here at school, but it gets even crazier at university. And this person, I love that they've added error values or error bars to their error. So I think this would actually be like 120% chance that their value is going to fall within that range because they've increased their error bars. So I just thought that was funny. Weird sense of humor. That's from the website XKCD, by the way, if you like maths and science comics. Okay, so the other thing that we have to calculate is the percentage uncertainty. So for example, let's use my example from before. Oh my gosh. Okay, let's try that again. So let's take our measurement from before. So we have 0.1 was our uncertainty. And let's say we measured our 0.5 litres. So the percentage uncertainty would be the absolute. So that would mean like it doesn't matter if it's positive or negative. We're just going to put the absolute brackets around it. Divided by 0.5 times by 100 to make it a percentage. And that is going to be 20%. So it's 20% uncertain, which is, you know, pretty reasonable considering we're measuring half a litre with these 100 ml increments. So it's not the most accurate way of measuring. All right, so the impact of uncertainty. So why does this even matter how uncertain something is? Well, we have to know whether or not the experiments that we're performing are going to be consistent or if they're going to be discrepant. Because if they're discrepant, we might want to repeat the experiment or repeat the measurements so that we can have the most accurate and most precise results for our experimentation. So let's have a look at this question here. So identify which measurements are consistent with the rulers in figure 3. And so what we would do is we would actually work out the values for each of these, or the ranges for each of these. So what I mean, our first one is for plus or minus 0.1. So that's going to be from 3.9 centimeters to 4.1 centimeters. So our measurements are going to fall within this particular range. So I'm going to go ahead and do that for each. Okay, so I finished calculating each of those ranges. So I've just added or subtracted each of those uncertainties from each measured value to get these ranges. And then what I've done is I've just had a look here. Now this ruler, the smallest increment of measurement is 0.5 centimeter. So the accuracy of this ruler would be plus or minus 0.5 centimeters. So having a look here, this is falling somewhere within the range of 4 to 4.5. So that's what I've just written here. Now, if this is consistent, that means it's going to overlap. And just having a look here, so this has some overlapping values because it overlaps from 4 to 4.1. This definitely has overlapping values because it's from the range 4.2 to 4.4. This has a little bit of overlapping values here, so that would go from 4 to 4.05. So yes, that would be consistent as well. And then this last one here, 4.25 to 4.35, also falls within that range. So ruler A, the measurements are pretty consistent with that ruler. So you can go ahead and do the ruler B for me, and I'm going to let you figure that out on your own. It's not really too tricky. I don't think I need to harp on about that one too much. Okay, so combining uncertainty. This is where it gets a little bit kind of crazy. And so I've drawn this diagram just to sort of help you visualize what's going on here. So when you actually combine uncertainty, so let's say I had a measurement of like 10 centimeters plus or minus 1 centimeter, and then I had another measurement of 9 centimeters plus or minus 1 centimeter, and then I added the two lengths together. So an example of this might be that your ruler, like I know a lot of you don't have the 30 centimeter rulers, you've only got the 15 centimeter rulers, so then you would have to do the measurement twice. And so, oh my gosh, everything is going off today. And so because you would have to do the measurement twice, you've effectively incorporated two lots of uncertainty into your actual measurement. So what we do when we're adding these uncertainties, we're going to use a variation of Pythagoras' theorem. And Pythagoras' theorem is c squared is equal to a squared plus b squared. And I've drawn a little diagram to show you why. So what I've done is I put my, my value for a on the x-axis and I put my value for b on the y-axis. And this would be, if I added the points, this would be the total error potentially, or the range of error potentially for this particular measurement, because each of them have plus or minus 0.5 mils. And so if I wanted to work out the length of this line here, well, this is a right angled triangle. So what I could do, this here, I could define as my base. So we could make that A. We could make this height along here our B. And so therefore our complete error, or our total error, is going to be this value here, C. Okay. And so if we wanted to find the value for C, C squared is going to be equal to A squared plus B squared. And so our value for our error is going to be the square root of A squared plus B squared. So that's where that idea comes from. So let's go ahead and do the error. So this is going to be the question B here, determine the absolute uncertainty of the combined volume of reactants. And luckily for us, we have A is equal to 0.5 and B is equal to 0.5. So to find this error term, when we've added this, we're going to substitute into the formula A squared plus B squared. Always doing FSA, formula, substitute, answer. So next, substitute in the values that we know. So we know that A and B are both 0.5, luckily. And then we're just going to perform that calculation. The combined error, or the combined absolute uncertainty of the value of the volume of the reactants, is going to be plus or minus 0.7. Okay, so let's go ahead now and let's find the combined volume of the reactants. So I'm just going to add 15.3 to 18.5. So this is going to give me 5 and 8 makes 13, and then we carry the 1, 33.8 plus or minus 0.7 mils. So that was our combined volume of our reactants and our absolute uncertainty. Lastly, we're going to use our answer from part B to determine the possible range of the combined volume of the reactants. And we've done this a little bit now. So all I'm going to do is I'm going to add 0.7 mils and I'm going to subtract 0.7 mils. So our range will be anywhere from 33.1 to 34.5 mils. All right, let's move on. Let's talk about some more types of error. So parallax error. Now, parallax error is a type of systematic error. Parallax, if you did not know, there's an episode on Star Trek Voyager. If you haven't seen Star Trek Voyager, you need to go check it out. There's not any like big crazy explosions or anything like that, but it's really interesting because I think it's more like intellectually stimulating, and it's really cool to see all these different planets that they go to and like the perspectives of people on the different planets and why they have those particular viewpoints. And so parallax error primarily is a perception error. This bell, oh my gosh. So parallax error is a type of perception error. And this particular episode, what happens is that they go to this planet because they think, oh no, this planet, it's in peril. We've got to go and save these people. And so the Star Trek Voyager team, they go to the planet and they actually work out that they've perceived the situation wrong and now they're in great danger and they have to go and try to save themselves now from this situation that they've got themselves into. So parallax error primarily is a perception error. I've got this little diagram here just to sort of show you what I'm talking about. So when we measure volumes of any sort of reactant that we're dealing with, we must make sure that we get down onto the same level as the measurement so that we are looking at this measurement straight on. And if I look at this measurement straight on, it's actually got a volume of 3 mils. Now, parallax error, perception error, right? So I've got this guy, and this guy, he's a lazy person. He doesn't want to bend down to have to look at the measurement because, like, he doesn't have to do that. He's too cool. And so he's just going to take, like, whatever measurement. So he's just going to look at this measurement here, and then he's going to go, yep, that's accurate. That's 2 mils. That's done. And that's not actually the case. And so this person, when they go to perform their calculations later on, they're actually probably going to find that they have a lot of error associated with this. And I saw this at university all the time, people who do not know how to measure things correctly. And then they would look at their models and they would say, oh, geez, these models are really, really poor. I wonder why that is. And I would think to myself, oh, thank goodness I had my mean, nasty chemistry teacher who would get on us about making sure that we were doing things correctly, because she had her PhD, so she knew how to work in the lab. So it's really, really important that we actually get down to that level. Now, let's say on the other end, we have someone who is a little bit of a shorty and they have a little bit of difficulty seeing up to the bench level. Maybe they should get a team member, a taller team member to help them out. And what they do is they have a look and they're trying to see this measurement here. And to them, it actually looks like it's going to be 4 mils. And again, this person might find that they have a lot of error associated with their measurements. So parallax error is this perception error, and this is a systematic error, or a random error. And we can actually correct for this one by making sure that we are performing these measurements correctly. So that's all I want to say about parallax error. We don't have to calculate anything for that one, luckily. All right, so percentage error. This is the last little topic that we're going to talk about today. So percentage error is just the difference in our expected value compared to the actual value that we've measured in real life. And this could be a result of us not performing the particular techniques correctly. The other thing might be, like, for example, with measurements, such a simple mistake. When people are measuring out particular amounts of reactants on a scale, they'll pop the beaker on and they won't tear the scale. They won't put it back to 0. What they'll do is they'll just dump their stuff in, and then they'll go, oh, I've got 100 grams of this. And it's like, no, you don't. You've got the weight of the beaker included. So it's just simple little things like that that are going to result in these errors. And we want to know as scientists, how well we've performed these experiments and how accurate our results are, because science is really just the pursuit of truth. And if we're doing this in an inaccurate way, then we're not going to get the results that we want, and we're not going to progress forward in our scientific endeavors. So let's have a go at this percentage error. So a student measured the volume and mass of an aluminium cube and calculated the density of the aluminium to be 2.67 grams per cubic centimetre. They researched the density and it was actually 2.7 grams per cubic centimetre. Calculate the percentage error of the measured density. So we're going to do this using an absolute value. So absolute value just means we're going to pop these brackets on the ends here. So first things first, as I said before, we write our formula, then we're going to substitute, and then we're going to get our answer. So percentage error is going to be equal to the difference between the measured value and the true value, divided by the true value times by 100 to make a percentage. So let's substitute in the values we know. So we know that they measured the density to be 2.67 grams per cubic centimetre, and the true density value is 2.7 grams per cubic centimetre. And we'll divide that by the original value, or the value that it should be. We'll put our absolute brackets up the top and then times by 100 to make a percentage. And our percentage error works out to be 3%. So what I can do now is I can express this. So let's say we do 2.67 plus or minus 3%, because we did have a bit of error. If we were to add this to another value, so let's say he did the experiment again and he got 2.5, and then he had a percentage error of 2% for this one. And let's say we wanted to add these two volumes together. We're dealing with a percentage now, so it's going to be a little bit different. So what we would do is we would actually add the two values, so 2.67 plus 2.5, and then we would add the percentages as well. If we were to double this volume, the percentage would still remain the same, because it's 3% of the entire thing. All right. So let's go through a couple more examples, and then I think we'll finish off. So you guys can go ahead and do number 1 on your own. We've also gone ahead and done number 2, so you're doing ruler B on your own. Question 3, identify the ranges of values suggested by the measurements 10.3 plus or minus 0.8 seconds. Again, I think you can go ahead and do this one on your own, because you're only going to add or subtract 0.8 from your measured value. Okay, so question 5, a student measures the volume of a liquid in a volumetric flask and as a measuring cylinder as 16.3 plus or minus 0.3 mils, and then 15.9 plus or minus 0.2 mils. So this first one was the volumetric flask, and this second one was the measuring cylinder. Okay, Determine the ranges of values for each container. So again, that's just the same process. So I would add and subtract 0.3 to get the range. I don't need to do that for you. You can do that yourself. Classify the measurements as consistent or discrepant. So remember what we're going to do when we calculate that range. This is going to go from 16 to 16.6, and this one here is going to go from 15.7 to 16.1, and so there is an overlap, and so therefore they are consistent. Question 6 we've actually gone and answered previously. Let's have a go at question 7. So a student weighs themselves on some scales and they read their weight as 70.5 kilograms. So what that means is I'm assuming that this scale can measure either to the nearest 0.5 kilograms or it can measure to the nearest 0.1 kilograms. So assuming the scale is accurate, determine the absolute uncertainty for the student's weight. So it depends on the scale. I'm assuming this is going to be the measurement because that's pretty typical for scales. So we would write this as 70.5 plus or minus 0.1 because that's the smallest increment that the scale measures. And so therefore determine the percentage uncertainty for the student's weight. So that's just going to be the uncertainty divided by the weight times by 100 to make a percentage, and that's going to give you my answer, 0.14%. Does this seem reasonable? Yes, it does, because if I'm weighing, and this is a 0.1 absolute error, and I'm weighing 70 kilos, I mean, that seems pretty reasonable to me because this measurement is so small compared to the value that you're measuring. And that's a good trick too. So if you can, if you're measuring like very small values, then you should have very small percentage uncertainties or absolute uncertainties. Okay, next question. Question 8, a student wants to determine the volume of a rectangular container. They use a ruler to, with an absolute uncertainty of plus or minus 0.2, and they obtain the following measurements. Analyze the information to determine the percentage uncertainty. We've just done that, so you guys can go ahead and do that yourself. To calculate the volume, the student multiplies the length times the width times the height of the container. So when you are multiplying, you just multiply all of those values because you're multiplying the error as well. You're not adding those values, so therefore you wouldn't use the c squared equals a squared plus b squared formula from before. You'll just multiply all of those values. And then determine the percentage uncertainty and then can find the percentage error. So I think you guys can go ahead and do that one yourself as well. Pretty straightforward processes, to be honest. All right, so I might just leave it off there then, and I will talk to you guys in the next video. So looking at constructing and using graphs. Talk soon. Bye, guys.